To start out our study of quadratic functions and looking at things in a little bit more depth, we're going to take a look back at some of the characteristics that we discussed in our first unit, such as domain and range. We're going to add one new idea in and start looking specifically at just the characteristics that go along with quadratic functions. So to start out, we have three different versions or three different forms of quadratic functions that we can use. So the one that we're already familiar with is our transformational or vertex form. And so that's going to be in the form f of x equals a times x minus h squared plus k. So we can use this as long as we know what our vertex is, and we can determine, do we have a stretch or a shrink? Do we have any reflections or any shifts left or right compared to having our parabola or quadratic sitting right at the origin? So if we look at our example, we have a parabola that looks like it's been reflected upside down. So it's been reflected across the x-axis. It has its vertex at -1, 4. And it does look like that we're not stretching this at all. I can go from my vertex down 1 over 1, but I'm only going over 1 unit. So I can tell that this is not going to be stretched. It's not going to be dilated vertically, but I do want to take into account that it got flipped upside down. So to write this in transformation or vertex form, we would write it as f of x equals -1 times x plus 1 squared because it got moved to the left 1, and plus 4 because it got moved up. We can also look at this now in terms of factored form. And so you'll notice that all three forms, your transformation or vertex form, your factored form, and your standard form, they all start with that same letter A. And in fact, when we're looking at our different forms, that A value is going to be the same no matter what format we're using. So I know right off the bat, in my factored form, my A is still going to be a negative or -1. And then the R1 and R2, which we'll actually explore a little bit more in coming lessons, those are our roots, otherwise known as X-intercepts or zeros. So I definitely have two X-intercepts or zeros on my graph. I have one hitting at -3, 0, and one hitting at 1, 0. And so with the factored form, similar to what we put inside our parentheses with our vertex form, we're going to subtract each X-intercept. So our format would look like x minus a -3, aka x plus 3, and x minus 1. Now to get our standard form, which you'll notice looks just like the quadratics we were factoring last unit, we could actually multiply out either one of our other forms. Now I tend to go easiest from factored form out to standard form. So if I took my factored form and multiplied it out, and so actually distribute out the x plus 3 first, keeping my -1 out front or the negative out front. So distribute your x, you'd get an x squared, multiply the x over the -1, so minus x, then distribute out your 3. Then all we would need to do is combine our like terms, which would give us a positive 2x, but then we have to multiply everything by the -1. So this function would actually read out as -x squared minus 2x, because again, -x plus 3x gives us a positive 2x, multiply it by -1. And then a -1 times -3 would give me a positive 3. Now notice too that 3, that also corresponds with our y-intercept that's on the graph. Now, keep in mind, if you ever get stuck on picking out your different points, your different characteristics on your graphs, don't forget you can always go through and graph these out. So if I actually switch over to Desmos calculator, don't forget the easiest way to do this is just type it straight in. You can actually use f of x if you'd like, or you can type in y. I'm going to type in y because I'm on a touchscreen computer right now, and that works a little easier. So if I'm going to graph this out in standard form, just to make sure that I wrote it out properly, I would graph out -x squared minus 2x, and then plus a 3. And I forgot my negative in there, so let's put that in. And so it flips it around perfectly, gives us exactly the same points as we had before. And again, don't forget on Desmos, one of the really neat features is you'll notice it has all those points marked already on the graph, the same ones that you have on your notes. And so if you click on each individual point, it will actually give you those coordinates so you can read them off. So I can see very clearly I've got my vertex at -1, 4. I've got my Y-intercept at 0, 3. And I have X-intercepts at 1, 0 and -3, 0. And you could actually, if you want to, check out all your other forms. So let me just go ahead real quick and graph the other forms just to see if everything matched up. So our factored form was -x plus 3. And then we had an x minus 1, and it puts the graph exactly in the same spot. So I know I graphed that properly. And then let's try our original version. So y equals, again, a negative. Then we have an x plus 1 squared, and then a plus 4. And yet again, it's all on that same parabola. So great way to check your work on this. And again, any graphs where this would be appropriate for you to check versus your graph versus your equation versus your properties, we'll always embed that in whatever practice that you're doing online. Or if you're just doing a straight out practice that you're maybe writing out, you can always go to the web address that you see up at the top, desmos.com/calculator. Okay, so let's go through some of the properties on here. Let me go back to my notes file. So let's list out the properties. And again, because these are all three equations, they're still for the same function, the same graph, the properties aren't going to change. So let's just list these out. So your vertex, again, is that very topmost point, and that was sitting at -1, 4. For the question max or min, think back to when we talked about absolute minimum, absolute maximum. And because this is the very top of the graph, this is an absolute maximum. Our y-intercept was sitting at the point 0, 3. Our domain, again, we can plug in any x value we want. So that's x such that x is in the set of all real numbers. Our range, our y values, or f of x, is such that, well, f of x is anything below that vertex. So we're less than or equal to 4, because that was the y coordinate of our vertex. Then we talk about interval of increasing and decreasing. So again, this is where we use our interval notation. We're increasing on the first half of the graph. So everything from -infinity to, again, our x value, so -1. And again, I'm thinking of this as I'm walking left to right. So the interval of decreasing, once I hit that vertex and start walking downhill, that's where my decreasing is, picks up again at -1 and goes on to infinity. We've also already talked about end behavior. And so that's always set up as x approaches infinity and as x approaches -infinity. But no matter what on this graph, both ends keep going down towards the -infinity on y. So we can say that in both cases, f of x approaches -infinity. Our x-intercepts, otherwise known as roots, otherwise known as zeros, we're sitting at -3, 0 and 1, 0. And again, we're going to explore a lot more with that in the coming lessons. Keep an eye out for that on Wednesday's video. Our new piece, so you might want to highlight this. I'm going to put it in a different color. New piece is axis of symmetry, which you may or may not have talked about in Algebra 1. So the axis of symmetry, I'm going to scroll back up. Think about that word symmetry. So you talked about symmetry in geometry. And when you have a line of symmetry, it's really just a line that goes kind of through the middle of a figure, or it splits it perfectly in half. For this, our axis of symmetry that would split our parabola perfectly in half is going to go right down through the middle. And you'll notice it intersects that vertex. And so all we would need to say is, what's the line that I could graph to make that happen? Since he's a vertical line, it's always going to be x equals. And so if it's going through the vertex, well, what's the x coordinate of your vertex? Well, that's just -1. So if you already know what your vertex is, you can figure out what the line of symmetry will be. So let's go back to this a value. So again, you'll notice that every single one of these forms has an a value, the very same a value, in fact. So whether you're working in your vertex form that you're used to, or factored form or standard form, no matter what, that A value is always going to be the same. So the rules that we talked about in our first unit are always going to hold true. So if A is greater than 1, we're going to have a vertical stretch. So all of your Y values are going to be stretched out from the origin, or out from your vertex technically. If you have your absolute value is between 0 and 1, so you have a fraction, you're going to have a vertical, you can call it a shrink, or a lot of times I'll call it a compression, where you're kind of pushing things in towards your vertex. And then if that A value is negative, like our example that we just did, that means we're going to have a reflection. I can't spell today. Let's fix that. Reflection over the x-axis. And again, we will not do reflections over the y-axis too much. We're really leaving that more for future classes. Alrighty, so first set of examples, we're going to write each quadratic function in factored form. So really all that means is we're going to factor each expression. So this piece is really just reviewing what we did last unit. And then that will allow us to state X-intercepts, which we're going to practice a lot more over the next 2 days. But just to give you a preview. So in expression 1, if we're going to factor that out, again, my x squared, I know the only way to multiply that or to get factors would be x times x. 2, the only way to get that is 1 and 2. And so we just need to know what our signs are to get that positive x in the middle. We would want a positive 2 and a negative 1. And so with our zeros, again, think about what number we would subtract. I'm going to go ahead and write in my factored form just for comparison on this one. So it would look like a, x minus our first root, and x minus our second root. So that means that our roots, well, x minus 1, so 1 is one of the roots. And then x plus 2, well, I would have had to subtract a negative 2. So kind of like what you're thinking of when you're doing your horizontal transformations in your vertex or transformation form. Alrighty, example 2. Again, if we're going to factor this out, always look for what step first. Now look for a GCF first. And so this is going to be, I can factor out a 2, which would leave me with an x squared minus 9. And then this is actually just a factoring pattern. So this was our difference of squares. So we have x plus 3 and x minus 3. And so our roots on this one, again, what number do you have to subtract to make it look like x minus something? So our first root is actually negative 3. Second root is positive 3. Okay, h of x, again, always look for a GCF first, and we're not used to factoring, with that negative out front. So I'm actually going to factor out a negative 1 from everything first, which will indeed flip all my signs. And then it's a lot easier to factor because I'm noticing too, I have the x squared, so we're leading with the x's. 9 is 3 times 3, which would absolutely get me to that 6. And so this is one of these cases actually where we're going to have the same number as a root. So our roots are both 3. And so we're going to look a little bit more in depth over the next 2 lessons about what that really means and what these expressions are going to look like when we start graphing them and solving them. So keep that in the back of your brain. Okay, a couple more examples where we're just going to sketch out the function and state out its characteristics. So again, with these, if you're not quite sure what the picture is, go right back to Desmos. Now, number 4, I can graph this without any help because this one is already telling me where my vertex is going to be. I'm going to have to shift it to the right 4 and down 2. Actually, let me switch to red so it pops better. So I know my vertex is going to be here. And I also know I have this A value of 2. That means I'm going to stretch it twice as tall as it should be. So instead of just going over 1, up 1, I'm going to go over 1, up 2. And then I can kind of continue that process. But for now, I'm just going to sketch it in. And again, it kind of looks a little bit narrow down at the bottom, but the big thing is, do you know where all the important points are? So our vertex, we already found that. That was 4, negative 2. which means we already know our axis of symmetry, x equals 4. Our domain for any parabola, for any quadratic function, is always going to be all real numbers. So x is such that x is in the set of all reals. And our range is going to be anything above that vertex for this one. So that means we're going to be f of x is such that f of x is greater than or equal to that y value, the vertex -2. Then we keep going. So now that we know that our vertex is sitting at the bottom, well, wait a second, that means that that's going to be a minimum. So that's an absolute minimum. Our X-intercepts, we already graphed because we were using that idea of how far it stretched. So those are hitting at 3, 0 and 5, 0. So this next piece, the Y-intercept. Yeah, I don't quite have enough room on the graph. So let me jump over to Desmos to do that one. So let's go back to Desmos. I'm going to clear out my previous functions. And let's just type this guy in. So y equals, and then we had a 2x minus 4. And again, you'll notice nice thing about this is it does kind of update real time. So you can really, if you get stuck, you can kind of see what each function or each constant does. And so there's my function hitting at the same points that I predicted, but my y-intercept is way far up. So nice thing about Desmos is I can just drag it until I get all the way. Wow, this guy's really tall. If I hover right over it, again, it'll tell me, is that a correct point? Yep, it's hitting at 0, 30. Okay, so let's go back to notes. So y-intercept is at 0, 30. Okay, interval of increasing and decreasing. Again, it starts on the left. If I just start walking left to right on my graph, I'm walking downhill first. So I'm actually going to do decreasing first. He starts at -infinity and goes all the way up to the x value of your vertex, which is 4. And then interval of increasing picks up back after that. So 4 up to infinity. And then our end behavior, both ends keep going up. So it doesn't matter if we're looking at as x approaches infinity or as x approaches -infinity, both of these, our f of x is going to approach positive infinity. Alrighty. So again, pause, rewind if you need to get that down. If I'm talking too fast, you can always kind of rewind, rewatch, or slow me down. Let's look at our next one. Okay, so I can cheat a little bit on this one because I know what it's supposed to look like for graphing, but we really haven't practiced factored form. So again, let's just go back and graph it. Okay, so new function. And again, if you're on a touchscreen computer like me, just hit this little keyboard icon and it will pop up with your keyboard that you can use. So our second function, again, you can do the g of x if you've got a keyboard, but you can always just type y equals. We have negative, and then we have two sets of parentheses, x minus 2 and x plus 2. So hit enter, and I scrolled all the way up on my graph, so I'm going to go ahead and scroll back down. Again, you can just click and drag if you're on your laptop. Alrighty, so we have some really nice points here. So we have our X-intercepts sitting at -2 and +2. And we have a Y-intercept sitting at 0, 4. And that's everything that we need pretty much. So go ahead, take a moment, sketch that in. Pause the video if you need to. And then let's list out our coordinates or our information. Okay, so sketching out, we had a point at 0, 4, and then we had points at -2 and +2 for our zeros. Alrighty, so that puts our vertex at 0, 4. Our axis of symmetry is just the x value at that point, so x equals 0. Domain is always all reals. Our range, since we're facing down, that means we're going for values that are less than or equal to our y at our vertex, aka 4. Alrighty. Because it's flipped upside down, our vertex is actually our absolute maximum now. we had X-intercepts at -2 and +2. And I have a tendency to always write these in coordinate form because I want to be very specific as to what the points are. Our Y-intercept, a lot easier to see on this one, that was 0, 4. Interval of increasing and decreasing, again, as we walk left to right, we actually start on the increasing. So from -infinity to the X value on our vertex, which was 0, picks up again at 0, and then goes to +infinity for decreasing. And then for our end behavior, because both of our ends go down in the Y values, as X approaches infinity, f of X approaches -infinity. And same thing in the other direction. And again, if you need to review this and look at these examples in other contexts, don't forget all of your materials are still unlocked for Unit 1. You can go back and review any of those videos or check out the YouTube channel. I have that linked under our course info, and you can just go through and watch whatever you need to help you review. Okay, now would not be a bad time to pause and try out the last example on your own. So again, gave it to you in standard form, and it has some decimals in there. So this would be a great candidate for plugging into Desmos. All right, so if you plug this into Desmos, you're going to find there are actually some pretty nice points on here. So we're going to have our vertex actually sits at 1, -2. And then we have one X-intercept hitting at 3 and the other X-intercept at -1. And so when I draw this in, again, it looks like it did get a little bit wider on it, although technically we were compressing it vertically. So this point here, we would expect to go over 1, up 1, and it really only went over 1, up 1/2 because of that 1/2 compression. Okay, our vertex is at 1, -2. So that means our axis of symmetry is X = 1. As always, our range for every single quadratic is always going to be all reals, domain, range, f of X is everything greater than our vertex. So greater than or equal to that -2. Because our parabola is facing up, that means our vertex is at the bottom. So it's an absolute minimum. So absolute minimum. Our X-intercepts happened at -1, 0 and 3, 0. Our Y-intercept, ooh, that one I need to double check, because if you go back to look at the graph, and you might want to go pause and go do that, again, it's not hitting at a very perfect number, but it actually isn't too bad. It ends up hitting at 0, -1.5. And again, you can just do that by clicking on that point on Desmos. Interval of increasing, because again, it's facing up. When I start on the left, I'm going to be walking downhill. So I'm going to start with interval of decreasing, -infinity to the X value of your vertex. So that means up to 1. And then at 1, it picks back up out to infinity for increasing. End behavior, because both of the ends are going up, it's exactly the same thing as the first example on this page. So as X approaches infinity, f of X goes to +infinity, and same thing in the other direction on the X's. F of X still approaches +infinity. So again, if you need any review on the characteristics besides axis of symmetry, absolutely go back and look at the materials from Unit 1 and Unit 2 with the absolute value. Everything is still open if you need to check it out. As always, let me know if you have questions, and if not, check out your practice. See you later.